rectifier, or it is commonly known as thyristor. So you are recording my lecture. Okay. Why I don't allow you to record my lecture is that I am not always formal with you in the class. So if you record something, I need to be formal in the class, right? So I don't like that. So that's why I never allow you to record my class. Okay, so anyway, as you can see here, the thyristor is basically a 4-layer device. So diode is basically 2-layer device, right? Transistor, it is a 3-layer device, right? But the thyristor, it has 4 layers: P1, N1, P2 and N2. So thyristor is basically 4-layer device, but it has 3 terminals. Okay, so now as you can see, this is the thyristor symbol, and in construction, the construction is given in this figure. So as you can see, this N plus region, it is highly doped. It has 10 to the power 19 concentration per centimeter cube, Richest concentration of that. Now you can see that. Now this layer is lesser concentrated as compared to the N plus region, and then the middle layer, which is known as N minus layer, it is the least concentrated layer among the 4 layers. Okay, and then the bottom portion, which is known as P1, it has 2 sections. So if you see there is 2 sections here. One has a 1 concentration as compared to the other ones. Okay, so why we put a less doped region in the middle, we will explain that in a short while. Okay, so now if you see here, suppose you have a thyristor and you put a voltage source, negative terminal of the voltage source to the anode. So this is my negative, this is my positive terminal. Okay, so now consider this device as a 3-terminal device. You have one resistor here, and then in between these two you have another resistor here, and in between these two you have another resistor like this. Okay, so now if you put these 3 resistors and you are applying a negative voltage here at the beginning and a positive voltage here at the end, so how this voltage will divide? It will be like this, right? 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 So for the first part, as you can see, your P1 is with the negative terminal as compared to the N1, right? Right? So the junction 1, J1, it will be reverse bias, right? Make sense? For junction 2, your N1 has less potential as compared to the P2 terminal, right? So what will happen? This junction, it will be forward bias, right? And for the bottom one, your P2 will be in less potential as compared to the N2 terminal. So what will happen to the J3? It will be in reverse bias, right? So meaning that the upper portion here and the lower portion here both will be in reverse bias, right? So meaning that there will be a lot of deflation here in this region. Right? Similarly, there will be lot of deflation here in this region, although this region, the middle junction, it will be forward biased, right? So since the upper portion and the bottom portion is in reverse bias, so what will happen? Is there will be any huge current through the device? There will be only a leakage current through the device in the reverse bias section, right? Make sense? So now what will happen if you change the voltage polarities? Suppose now a positive terminal is of the source is connected to the anode of the thyristor. So again, if you consider this to be the 3-terminal resistance like this, so now the voltage will be like this terminal will be positive, this terminal should be negative, right? Meaning that the voltage distribution should be like this, right? Make sense? Right? So now for the first part, your P1 will be operating at higher voltage as compared to N1. So what will happen to that Gen 1 junction? It will be in forward biased. Then for J2, what will happen? Your N1 is operating at higher voltage as compared to P2, right? So this junction, it will be in reverse bias, right? And then for the last one, P2, it will be operating at higher voltage as compared to N2. So what will happen there? It will be again forward bias. Now you have 2 forward bias region and 1 reverse bias region. So what will happen? There will be depletion here only in the mid junction, right? But again, there is a reverse bias section, right? So in that case, there will be a leakage current in the what? And the positive direction, right? So now if you increase this voltage, then what will happen? If you increase this voltage after a certain point, this point, what will happen? There will be a avalanche breakdown, right? So if there is a avalanche breakdown, so in that case what will happen here? This total depletion layer, it will disappear, right? And there will be a current through this thyristor, right? So the current, it will jump to a higher voltage, but at this time the voltage should be higher or lower? It should be lower, right? Because the thyristor has turned on, right? So for example, suppose you have a diode. So if it is not turned on, what happens to it? The voltage across it gets bigger, right? But once it is turned on, what happens to it? The voltage drops down, right? To some value, 0.7 volt or 0.3 volt, depending on the value of the material, right? Right? So once this diode is turned on, although the current rises to a higher value, what will happen to the voltage? The voltage will be dropped down, right? Make sense? But this is not the right way to turn the thyristor on, because whenever you have an avalanche breakdown, there is a high possibilities that that thyristor may get damaged, right? which can happen for the reverse bias region also, right? If you put a reverse bias voltage beyond this point, then what will happen? There will be an avalanche breakdown, and the diode, the thyristor, it will not work like a thyristor. It will be just a short circuited element, right? Makes sense? So there is no, then we should not put the voltage across the thyristor beyond this point, right? Where the thyristor will be at the brink of getting into the avalanche breakdown region. So how we can avoid that situation? Right. So how we can do that? If you put a positive pulse here, so this P2, suppose you put a positive pulse here like this. So what will happen? You will put these positive charge here, right? So in that case, this thing will force this depletion there to get disappear. Okay. So in that way, we can make this diode or the thyristor in the active region to turn that thyristor on. Make sense? So in the next thing, so whatever we have discussed here, it is from Nid Mohan's book. Nid Mohan's book. I forgot to just remember the page number. I will let you know. Okay. And whatever we will be discussing here, it is taken from Harun Rashid book. Harun Rashid book. Yeah, I will upload that today. So I will upload everything. You just need to read to do well in the exam, okay? Which is the most difficult thing to do for the students, because you have lots of things to do. Okay, I am being informal now, so I will not go into that one. So okay, so now as you can see, the thyristor, it was 4-layer device, right? So my P1, then we have N1, then again P2, and then we have N2, right? So now if I consider, if I divide this N1 layer into 2 half and P2 layer into 2 half, then we can think of this portion with one diode, right? Okay, so let me draw it with a different color. So now if I consider this portion, so this will be a PNP transistor, right? Right? And the lower half, it will be a NPN transistor, right? And the gate is connected here. And you have a anode here, you have a cathode here. So this circuit will be similar to this one, right? Right? So this is known as 2 transistor model of thyristor. Okay. So if I tell you to explain 2 transistor model of thyristor, you don't need to explain anything. You just need to draw this circuit.
That's all.
You don't need to say Dr. Harun Rashid has explained these things in chapter 10 of his book, where he tried to explain the characteristics of a thyristor.
So if you draw this was, so if you draw this one about
Yeah, just try to explain within 3 to 4 lines, not more than that. Try to write whatever is essential. Okay, you don't need to elaborate the thing. Okay. So now, so this is your PNP transistor, which is given here, and it will be connected to a NPN transistor which is connected here, right? Make sense? So you will have two transistors that will be back to back connected, right? Make sense? So now what will happen if there is no gate pulse here? What will happen if there is no gate pulse here? So suppose this thing is connected to a load. Suppose you have a load here and then you have a source connected to this circuit like this. So now if this source, it is in the forward bias, right? Forward bias resistor, because the anode is connected to the positive terminal of the source, right? And the cathode is connected to the negative terminal of the source, right? But what will happen if there is no gate current here? The current, this transistor is not turned on, right? This transistor is not turned on. If this transistor is not turned on, what will happen to your base current and the collector current? It is 0, right? So if it is 0 and this current is 0, then what will happen here? You don't have any gate current, right? So your base current here, it will be 0 as well, right? And this base current here, it will be the conductor current for this transistor, right? Meaning that if there is no base current here, there will be no collector current here, right? And the base current here is also 0, meaning that your current here, it will be 0 as well, right? Meaning that if you don't put any gate current, then what will happen? There will be no current through the transistor as well, right? Make sense? But if you put a positive pulse here, then what will happen? You inject a current here, right? So if you inject a current here, what will happen? There will be a base current here. If there is a base current, then what will happen? There will be a cathode current, right? This cathode current will flow, and if there is a base current, there will be a collector current here as well, right? And this cathode current, it will flow into this terminal, and there will be a IA current, right? If there is a IA current, what will happen? There will be a IP current again, and there will be a IC current, and this IC current will be much higher than your gate current, right? So your IP current will increase. If your IP current is increasing, then what will happen to your IC2 current? It will increase, and then your cathode current, it will increase, right? So if your cathode current is increased, then what will happen to this? IA current increase, right? If your IA current increase, then what will happen to this? This current will increase, and in turns this current will increase, right? And then it will cascaded. There will be a cascaded reaction until unless it reaches to a operating point, Q point of the circuit, right? Sorry? Yeah, it will keep increasing, but depending on the value of this resistor, it will increase up to a certain point, which is known as the load line, right? You have done that, the Q point operation for all the electronic circuit, right? So it will not keep increasing like the infinity, right? It will increase up to a certain point when the circuit will get settled, right? Make sense? So now once the circuit gets settled, if you put a negative signal here, what will happen? Negative current, there will be a negative current, meaning that the current, instead of going inside the circuit, it will come out. But this current, it will be much lesser than this IC1 current, right? So in that case, will the circuit be turned off, or it will keep? No, it will not decreasing gradually, because this current, it will be much lesser as compared to your IC1 current. Because this current is very less, so in that case the transistor it will be in the on state forever, until unless you make a thing such that this IC1 current is diverted to some other circuit. Okay, so in that case what is saying? Right, because if this current is beyond this point, if the current is beyond this point, that is known as the holding current, then you cannot stop the thyristor until unless you divert the current to another circuit. Whatever current is going through the thyristor, if you don't divert the current through another circuit, the thyristor will keep turned on. Make sense? So what is happening there? Why, if you have a current that is less than your holding current, the thyristor is stopped, and if the current is over your holding current, the thyristor keep turned on. Why is that? Any explanation? So, yeah, I am saying that if you see this characteristics, it says, or even in your book, it says if your current through the thyristor is less than the holding current, it means that the thyristor will eventually turn off. But if the current through the thyristor is over the holding current, the thyristor will remain turned on even if you put a negative voltage across it. Why is this happening? This is happening because, as you can see here, this middle region, it is lightly doped, right? Lightly doped, right? So if it is lightly doped, so the free charge concentration here, it will be very less, right? Meaning that if the current is very high, there will be high possibilities that all the current, it will just diffuse through the portion without being combined with the free charges available in this region, right? But if your current is less, what will happen? There is a high chance that all the charges will get recombined, that, right? So that's why it is said, if your charge or the current is less than this value, then there is a possibility that all the charge will get recombined in this region.
Sir, can you repeat the part of recombination?
Yeah, sure. Suppose, let me give you a numerical example. Suppose you have a total charge carrier here, positive charge carrier 150, okay? And suppose that current flowing through this layer, it has a concentration of 600 or 700. So although 50 of them will be combined or recombined, the rest of them will diffuse the layer easily, right? Because the current that is passing through that layer, it is very high as compared to the free charge that is present in the layer, so that they can get recombined, right? I say, suppose total charge particle that is flowing through this layer, it is 750, for example, and you have a free charge here. Free charge means the possibilities of getting recombined, it is already 50. You have probable free holes that can recombine with the electron, it has 50 particles like this. So how much it will get recombined? Maximum 50, right? But the 700, rest of the 700, it will easily pass through, right? Make sense? But if this is 50 and the current or the charge that combines the current, it is around 75. then what will happen? Most of them will get recombined, right? And if it gets for a 2 or 3 cycle, you can easily think that the thyristor will get turned off, right? Because this portion, the upper portion is forward biased, right? The lower portion is also forward biased. So the only problem it will face in this region, right? It needs to pass through this layer, right? So that's why it says if your current is below this holding current means what? This layer is trying to hold all the charges to get recombined, right? So if this current is below that point, then all the current or the charge it will get recombined, right? And if the value is more than that, then although it will get some recombination, but still you have enough charge to continue the current through the device. Make sense? Any question? Any question? Okay. So now, if you say, see here, so I think you have studied, already know these two equations, right? Your collector current and your, okay, just give your attendance in a blank sheet, okay? I forgot to bring the attendance sheet today. Okay, so now, do you know these two equations? What is your alpha? Common emitter current gain, right? And this part, it is known as the leakage current component, leakage current that is flowing from base to collector to base. Okay. So now, here as you can see, what is your IA? IA should be your IB1 plus IC1, right? Your IB1 should be what? Sorry, IA should be what? Your IB1 plus IC1, right? This current plus this current, right? Your IA current, this current should be this current plus this current, right? So we can write IA, we can write it as IB1 plus IC1, right? So what is my IB1? That is the current that is going into the collector of Q2, right? So instead of IB1, what we can write? IC2 plus IC1. That should be my IA, right? Any question? Any question? Do I need to write it down in another page? Okay, so let me draw it in another page. So suppose you have a Is there any problem understanding what I am discussing today? Okay, so now this is my current IA that is going inside this, and it should have two common terminals, right? This should be my IB1 and this is my IC1. This is my Q1 that has a coefficient alpha 1. Okay, so what should be my IA? IA should be my IB1 plus IC1, right? So IA we can write it as IB1 plus IC1. Okay. So now if I suppose this is my gate terminal G and the current I am putting here is my IG, and you have a this is my IK current and this thing is connected here. So this is my IC2, this is my IE2, and this is my IB2, this is my Q2. Okay. So now what is my IB1? It is same as your IC2, right? So instead of IB1, what we can write? IC2 plus IC1, right? That is my current IA, right? Now, if I want to write IK, what is my IK? IK should be what? My IB2 plus IC2. What is my IB2? What is my IB2? IG plus IC1, right? IG plus IC1 plus IC2. What is my IC1 plus IC2? IA, right? So we can write IG plus IA. That should be my I2, right? So this is this equation, right? And here from, if you use this equation, we have already discussed that here, right? Right? Your IA was what? IC1 plus IC2, right? Now if I put this IC1 value and IC2 value here, what we can write? Alpha 1 IA plus I CB01 plus alpha 2 IK plus I CBO2, right? So we can write alpha 1 IA plus I CBO1 plus alpha 2, what is my IK? IG plus IA, right? IG plus IA plus I CBO2, right? So now this is my IA. So if I keep all the IA terms in one side, what we can write? IA minus alpha 1 IA minus alpha 2 IA, that we can write it as 1 CB01 plus I CB02 plus alpha 2 IG, right? Or finally we can write IA, it should be I CB01 plus I CB02 plus alpha 2 IG over 1 minus alpha 1 plus alpha 2. So from this equation, what we can see here, our alpha 1 and alpha 2 value, summation of these two, it should never be 1, right? Otherwise you will have infinite current through the thyristor, right? And another thing is that whenever there is no gate current, if Ig equals to 0, then from this equation what we can write? Ik equals to IL, right? From this equation. Right? So whenever there is no gate current, whatever current that is going out through the transistor, it should be the same current that is going into the thyristor, right? So the two key points to remember from the thyristor operation is that once the thyristor is turned on, it will remain turned on until unless you divert the current that is going into the thyristor through another circuit, although you have put a reverse bias across it. Because these two transistors, it will have a cascading effect on one another, so that will keep the thyristor on forever. And the only way to keep this thyristor turned on or make it turn off is that by any chance you have to make the thyristor to have a current that is below the holding current to make it turn off. Otherwise, it will not never be turned off. Sorry, I didn't get you. You are diverting this current to the ground. So, what is the benefit of that? For control turn off, you have other devices like GTO and others. So you can do that, right? But thyristor has some application that needs only the thyristor, not the other devices. Okay, we will discuss that in the using thyristor we can also divert the current as well without doing the short circuit connection or the giving connection to the ground. Okay, we will discuss that in the next class. How we can divert the thyristor current. So how much time we have? So that's why you have 30 minutes, right? So you are pretending like the Middle East friend we had. Whenever he got a low mark, he used to come to me and say, "Brother, we are Muslim." In America. So that's why he is asking me to give him, let him leave because it's the Asr prayer time. Okay. So now, is there any question regarding the operation of the thyristor or whatever we have discussed so far? Any question? This second phase onwards, it is taken from Rashid Zoo. And the first phase, whatever we discussed, it is from Neil Bohan. Okay. So now, suppose we have a simple circuit. You have an input source, V in, you have a thyristor, and now it is connected to a simple resistive load. So how this circuit will work? Suppose you have a input voltage, like this, and suppose you have a gate pulse Vg at some angle delayed alpha. So what will be my output voltage? So before you put a positive pulse at the gate, will that transistor will be on? No, right? So if the thyristor is not on, what will happen? Output voltage will be 0, right? But as soon as you put a positive pulse at the gate, the thyristor will turn on, right? So once the thyristor is turned on, so how the wave shape will look like? It will be the same as the positive half cycle for the remaining part, right? Now what will happen to the negative half? Should we have the negative part or only the positive half? Because it is a resistive load, so it doesn't have the inherent characteristics to store the energy, right? So the current, it should be similar to what you see, but its magnitude will be somewhat less than the voltage, right? Yeah, so what will be the current here? Your current here, I naught, it should be what? Your V naught over R. So the current wave shape will be the same as the voltage wave shape, but they will differ by the magnitude only, right? Right? And since it is a resistive load, meaning that there is no stored energy here, right? So once the current gets zero, meaning that this thyristor will be turned off, right? So in the negative half cycle, it will be turned off, right? What about the next positive half cycle? Right. So if you don't put another pulses, it will remain turned on, off forever, right? So in order to have a wave shape or repeated wave shape like this, you need to put the same pulses at an alpha delay like this. So here if you put another pulses, then again you will have the similar wave shape like this. No, they will remain turned on provided that the current through the thyristor is above the holding current. But here, since it is a resistive load, the current is going to zero, right? So that's why the thyristor is turned off. Make sense? So in that case, what should be your output voltage? V naught, it should be 1 over twice pi alpha to pi Vm sin omega t d omega t. Yeah, that's why I am the teacher here, right? I can make mistake, but you cannot. Yeah, right. Okay, so the same thing, if I use it for the RL load. So what will happen if I use the RL load with it? Suppose you have a sinusoidal waveform and then you have a thyristor and it is connected to a RL load. Suppose this is my V in, this is my Vg, and the voltage across it is my V naught. So what will be my wave shape like this? Suppose this is my input wave shape and we are putting a pulse here at some delayed angle alpha. So how my wave shape will look like? Not like that. So now, if I want to draw the wave shape, so what will happen? Up to this point, that thyristor will be turned off, right? Meaning that there is no output voltage here. So up to this point, it will be turned off, and then once it gets pulse, your output voltage will be similar to what we have like this, right? But what will happen to the current now? So now if I consider my current through this like I naught, so what will be my I naught? It will start from here, it will jump to a certain value, because unless this point it has a positive voltage across it, right? So the inductor current, it will be charging, and after a certain period of time, depending on the value of L and R, it will discharge to some other value, right? And in this equation you already know, whenever this T1 is on, suppose whenever this is my T1, so T1 is on, what will be the equation? So L into d I naught over dt plus I naught multiplied by R, that should be your Vn sin omega t, and we have already discussed how to solve this equation, right? So I will not go into that part again, because we have already discussed that part, right? So as long as your current is not zero, so what will happen? This inductor will need a path to get the current through the circuit until unless it becomes zero, right? Thyristor also wants that, because once the thyristor is turned on, it never tries to get turned off, right? He is very happy if it has currents through it, right? So in that case, until unless the current is going to zero, you will have the exact same wave shape as the input. Right? Because this inductor current is forcing this transistor to remain on, and until unless the current goes to zero. Actually, practically it should be turned off as soon as the current through the transistor is below the holding current. But we are considering the idealistic case, so we are considering that the thyristor is turned off once the current is becoming zero. Okay. So in order to, what will be my output voltage there? 1 over 2 pi alpha 2. This is my suppose beta. So this is my beta, this is my alpha. So it should be alpha to beta Vm sin omega t, and then it should be d omega t, right? So now if I want to avoid this portion, so what we can use? Freewheeling diode. So if you put a freewheeling diode here as well, so what will happen? This negative portion, it will disappear, right? Because all the inductor current, it will be circulating among this circuit, so that the current through the thyristor, it will be zero and it will be turned off, right? So without making a ground connection, you have other ways to divert the current through the thyristor, right? So we'll do that in the class. So how much time we have? 8. So it means 15 minutes, right? It means that the class is getting very boring to you. Okay. So I will just take 3 to 4 minutes, and then I will let you go. Okay. So today we will start another thing, but you have already studied that previously. That is the DC to DC converter we haven't discussed so far, which is known as flyback converter. It is also known as isolated converter. What is isolated converter? Why Why we need isolation? Why we need isolation? Have you ever heard the term isolation transformer? Because the circuit we have discussed so far, like the buck converter, boost converter, buck boost converter, choke converter, they are not electrically isolated, right? The output stage is directly connected to the input stage. They are electrically connected, right? But there are some occasions that before we used to see a bulb is connected with a TV circuit, so that whenever there is a high current, the bulb will get damaged, but there will be no damage in the TV circuit. Similar way, sometimes you might use a transformer, so electrically you just isolated load from the source, so that if there is any potential damage to the source side, it will not affect the load side. So that is called electrical isolation. So the flyback transformer or the flyback, if you have you ever seen the TV circuit, whatever circuit you have, the CRT TV monitor that we used to have before. So before, inside the TV there was a transformer whose name was flyback. Okay, so if you go to any mechanic that used to repair the TV, you will say that give me a flyback, they will provide you a transformer. Okay, so now what is my flyback converter? Basically it's the same converter that we used, but here we will use a transformer so that the source side it will be isolated from the load side. Okay, so now suppose for the flyback we will use a DC source, but it will be not directly connected to the load, rather it is connected to the load through a transformer. So that is my VS, that is my switch, this is my primary circuit, and what is my secondary circuit will look like? The secondary circuit will be like this with a diode, and then we will have a capacitor, and then this capacitor will be connected to the load. So suppose this is my V naught, this is my C, and the polarities of the transformer, you know the polarities convention, right? What is the polarities convention? If the polarities of one dot, it will be the similar of the polarities of the others dot, right? And for the transformer, it is a negative coupling device. It means that if the current enters in one dot, it will leave the other dot, right? You know this point, right? So what is the transformer equivalent circuit? What is the transformer equivalent circuit? What is the transformer equivalent circuit? So the transformer equivalent circuit is like this. Suppose you have a parallel branch that represents a core loss and magnetizing component, right? So this portion, it represents the core loss and there is a magnetizing component to it, right? And you will have a series component that will have R equivalent and a series inductance that will have a X equivalent. So that is the basic transformer equivalent circuit, right? Okay, so I don't have the intention to study further, but Why I want to stop here, because for the next topic or this topic, to understand the operation of this circuit, you need to know the equivalent circuit of the transformer very well. So before the class tomorrow, you just go through the equivalent circuit of the transformer, how you get the parameter, and then based on that we will start the class.